forgot my pen. Okay, so. No. So, derivatives. All right, derivatives of trig functions. But before that, we're going to do derivatives of inverse functions. Okay, so you don't want to miss this part. Okay, so back in the day when you learned about inverse functions, right? What did you learn about them? First of all, you learned that to graph an inverse function, you had to reflect the graph of f across the line y equals x, which meant, look, let me do it with like an exponential graph here. Like this was y equals e to the x. And then if I drew the line y equals x, okay, and I reflected that around that, what I would get is this, right? So that's a reflection around that red line. And this is the inverse. This is ln of x. It's the inverse. So that's how we would draw inverses. Another thing that we knew about inverses was if there is a point here, 0, 1, the corresponding point here was 1, 0. You learned all this in pre-calc and algebra 2. And the reason why that is because when you found an inverse, what did you do to the x and y? You switched x and y, right? If you have a function and we said find the inverse, the first thing you did was swap x and y. So that's what inverse does. It switches x and y. The domain and range get swapped. Everything gets swapped. So we have a function here, f of x. Okay? Suppose you want to find the slope at that point. Well, that's the tangent line. And remember, if I find the slope of the tangent line, that's the slope at that point. Well, the tangent line is just a linear, right, function. To find the slope there, I just do rise over run, remember? And I'm just going to make up some numbers. Suppose this is 7 and that's 4. So the slope there would be 7 over 4. Okay? Now, here next to it, we drew the inverse. And this is the corresponding point there. And now I want to find the slope there of the inverse. So the derivative, the slope of the inverse. Well, that's the slope of that tangent line right there. Well, look. If I were to find the slope there, compare the way the two look. What do you notice? What seems like happened there? It flipped, right? I see you guys like doing the flip. It flipped, right? It seems like the 4 is here now, the 7 is there. So it's like you're doing run over rise instead of rise over run, right? Right? Yes. So the slope here is 4 over 7. So what do we notice? When you take the inverse of the function, the derivative at the same point is the reciprocal. It's the reciprocal. Normal is the negative reciprocal. It's just the reciprocal. So when you go from function to inverse, okay, the derivative becomes the reciprocal. Okay? So let me show you in another way. Suppose you have x squared, okay? And this is the point, x equals 2, y equals 4. Okay? What's the slope, what's the derivative there? dy dx is equal to 2x at x equals 2. and, at 2 comma 4, that's 2 times 2, 4, right? Okay, but what if you took the inverse? The inverse is root x. The corresponding point now is 4 comma 2. Okay? So that's root x dy dx of root x. Trust me on this one, is 1 over 2 root x. Okay? So I did x to the half, 1 half x to the minus 1. So dy dx at 4 comma 2, how much is that? I ran out of room. 1 over 2 root 4. So that's 1 over 4. Right? So that's, yeah, it is kind of cool. So that's twice that we proved it now. Right? Look at what happened. So many things happened here. Look, so many things happened. Here, I did the derivative. The x value is this 2. Then I found the inverse. I took the derivative. Now the new x value is the old y value, right? So x is the new y, like orange is the new black, right? And then you get the same value but the reciprocal. Okay? All right. So let's move forward. Okay. We have this function x to the 5. Whoops. Plus 2x minus 1. The point 1, 2 is on the graph of f. We need to find the derivative of the inverse at 2 without finding a formula for the inverse. So I need to find the derivative of the inverse without finding the inverse.
So that's just the reciprocal, right?
Of the old function. So here's how it's going to work. We want it at x equals 2. Okay, so what do we know? We know that when in the original function, when x is 1, y is 2. And since we know that f of 1 is 2, right? This is the point 1 comma 2. We know that in the inverse, that corresponds to the point 2 comma 1. Okay? So what you want to do is first find the slope. Remember what we said here? That the slopes are just the reciprocals. So first find the slope of the original function. F prime of x is 5x to the 4 plus 2. F prime at 1 is 5 times 1 to the 4 plus 2. That's a 7. This is the slope at that point of the original function. Okay? At x equals 1. At its corresponding point, the derivative of the inverse is the reciprocal 1 over 7. Okay? Okay. No, that's the normal. See, that's the perpendicular line. This is the inverse. Okay. This is what you will see more often. F of 1 is 2. We don't even know what the function is. F of 1 is 2. Okay? So let's pair these up. F of 1 is 2. The derivative, the slope at that point is 3. F of 2 is 1. The slope at that point is 4. We want the value, we want the derivative of the inverse at 2. Okay? But remember, if this is the new x, it was the old y, right? If this is 2, 1 on the inverse, it's 1 comma 2 on the original. So it's just f of 1. Okay? So what's the slope at 1? 3. So f inverse prime at 2 is 1 over f prime at 1, 1 over 3. That's it. So these two are extra information. I am. Okay? All right. Yeah.
Just to clarify, you got
One more point about derivatives of inverse functions. If f is differentiable at every point, okay, of an interval, and df dx is never 0, then f has an inverse, and that inverse is differentiable. So first, let's unpack that a little bit. If f is differentiable everywhere, then so will the inverse. The inverse will be as well, right? Because when is f not differentiable? If there is a corner or a vertical tangent or a cusp, you know what I mean? So if f doesn't have any of those problems, neither will the inverse. So we're good at that. What's the thing about df dx never 0? So what does it mean if the derivative of something is 0? If the derivative of something is 0, that means there is a maximum or a minimum. And that means at that point the graph turns around, right? Look at that function here. Does that have an inverse function?
No.
So no. In Algebra 2, you learned to have an inverse function, something must satisfy the horizontal line test. So it shouldn't pass, a horizontal line shouldn't pass a graph more than once. The inverse of that, the way it looks, will look like this. Is that a function?
Yeah.
On the right? That's not a function. On the right here, is this a function? No. So this is what I'm saying. If the function looks like this, then the inverse will not be a function. Okay? Because the inverse is not like
that one's a vertical line test.
right, but it failed the horizontal line test, which means the inverse fails the vertical line test.
If it fails the horizontal,
Yeah.
it's the inverse.
But what about like horizontal? It's not like parabola. It's not a function. They don't have to be in square root.
It's not a function.
Positive and negative.
Yeah, it's a relation, but it's not a function, right? But so if the function itself, you know, does pass the horizontal line test and it's differentiable, then the inverse will be a function and it'll be differentiable. Okay, let's not worry too much about that. Let's move on to inverse trig functions. Okay, so we know, all right, I'm moving. We know,
That wasn't your daughter.
for that part it was. We now know all the derivatives of the trig functions, right? Sine, cosine, secant, cosecant, okay? What is the derivative of sine? Cosine, another trig function. What's the derivative of secant?
Secant x tan x.
Another trig function. Now we're going to learn derivatives of inverse trig functions. Good news is you only have to know for two of them, inverse sine and inverse tangent. But look, the derivative of inverse sine is not a trig function. It's just an algebraic function. 1 over square root 1 minus u squared. Okay? Yep. Times du dx, that's for the chain rule. The derivative of inverse tangent is 1 over 1 plus u squared du dx. Okay? If you really want to know why, here's how inverse sine looks. That's all it is, inverse sine. And its slope is not an oscillating function. Like, it doesn't change in an oscillating behavior. So there is no need for it to be a sine function. Okay, so you have to memorize these. That's, I mean, no sugarcoating that one, just memorize them. Okay? All right.
Will we never see cosine or?
No, it doesn't really show up. These are the big ones. Okay, so suppose you have inverse sine of root 2x. In here, this is the u, okay? So y prime is 1 over the square root of 1 minus u squared times the derivative of u. Well, okay, u is 2x to the half, right? Du dx is 1/2 2x to the negative half times what? 2. And that 2 cancels with the half. So it's just 1 over root 2x. Okay? Now, let's simplify this. This is 1 over root 1 over 2x, 1 over root 2x. It was square root. But now, so this is 1 over root 2x times root 1 minus 2x. And then you have to combine those roots. So 1 over the square root of 2x minus 4x squared. And I know a lot of you can like skip some steps from here to there, which is fine. The most common mistake here is students will just forget that the derivative of sine is that and the derivative of inverse tangent is that, and it'll just be like a whole other, you know, something that they make up. Okay, here, inverse tangent. This is the u, okay? So y prime is 1 over 1 plus x over 4 squared times what? What's the derivative of the inside? 1/4. Okay. Now, I'm going to do something unconventional. Work with me, but it really works for these. I'm going to rewrite that as 1 over 4 over that. Right? Because imagine if it was a fraction times 2. Could you have done 2 over this? It's the same sort of thing. And then you're like, okay, that, like, I don't know why you would do that. Well, because, look, this at the bottom is actually x squared plus 16, right? Okay? So the reason why I wrote the 1 over 4 over there is because, look, I can multiply this by 16 and this by 16. And then everything, like, magically becomes cute and not problemy. So in the numerator, I get 4 over 16 plus x squared. Right? That's it. Yeah. Are there any other ways to do it? Maybe, yeah. I mean, there are, of course, but that's an efficient way. So I like to, you know, show you guys that as well. Okay. A particle moves along the x-axis so that its position at any time t greater than 0 is inverse tangent root t. What is the velocity when t is 16? Well, v of t is x prime of t, which is equal to, okay, so if it's inverse tangent, 1 over 1 plus root t squared times u is root t, right? Okay? And at this point, I think we should all, you know, it's time where, if I have u equals root t, I think we've now reached a point where we could just automatically say, if u is root t, then u prime is 1 over 2 root t. Okay? You can do the process, t to the half, bring the half down, blah, blah, blah. You're always going to end up with that. So after a point, students see the, pattern, and if you can remember it, you could just use it. If you still want to go through the process, please do. Okay? Now, because this is an intermediate step, I still have to plug in the 16. I don't have to simplify it anymore, right? I could just say V of 16 is equal to 1 over 1 plus 16, right? The square and the square root go away, times 1 over 2 root 16. So that's 1 over 17 times 1 over 8, 1 over 136. Okay? Okay, last one. Oh, of course we have to find an equation of a tangent line, right? Okay. So for an equation of a tangent line, we need a slope and a point. Well, let's find the derivative here. 1 over 1 plus x squared is the derivative. At x equals -1, this is 1 over 1 plus -1 squared, 1 over 2. That's the slope. Okay, I need a slope and a point. I have an x, but not a y. So y at -1 is inverse tangent of -1. Okay, brings back memories. Where is tangent equal to -1? Where's tangent equal to 1? For what angle? Huh? You knew that. You do. Pi over 4? Pi over 4 is, where is 1? It's 1, right?
Oh, yeah.
But remember inverse tangent, but remember inverse tangent exists from -pi over 2 to pi over 2. So it's -pi over 4. So the equation of a tangent line then is y plus pi over 4 equal to 1/2 x plus 1. Whew. Tangent line.
I actually love tangent lines. I love it. It's kind of like free.
It's what?
It's kind of free.